Alright, so we learned some identities in our last unit. We're going to use learn and use more this unit. Okay? But these, well, all except for the last ones, these are the ones that we've already learned. You already know the reciprocal identities. You already know the quotient identities and the Pythagorean identities and the cofunction identities. You discovered these, believe it or not, in some of the homework problems, but we didn't really learn them as identities yet. Okay? So I want to take a couple minutes here to examine these even and odd identities, and if you understand what I'm about to share with you, remembering them will actually be really, really easy. Okay? So, first of all, let's look at what these identities do, and then we'll take a look at why they're named the even and odd identities, and that'll actually help us remember what they do. Okay? So, you'll notice here, starting out with cosine, when actually looking at all three, notice that the reciprocal functions follow the same pattern that their reciprocals do. So cosecant does the same thing that sine does. Cosine does the same, or secant does the same thing that cosine does. Tangent and cotangent do the same things as well. And the key here is what we're looking at with even and odd identities is we're looking at cases where we make the angle negative, okay? Or what effect does making the angle negative have on the value of our function? Okay? In the independent practice, we had a couple that kind of forced you to think your way through these. Now we're actually learning these as specific identities, okay? So looking at cosine here, what we find is that the cosine of a negative angle is the same as the cosine of the positive angle, okay? Now, think about your cosine function here. And I'm actually going to draw two periods of it, one to the left and one to the right, so we can see some negative angles. Okay? So here's two periods of my cosine function. What is the cosine of, let's go with 5 pi over 4?
0?
No.
Negative 1.
No.
1.
5 pi over 4.
Only 3 options.
0.
Here's 5 pi over 4.
So, like,
What?
Negative root 2 over 2.
Negative root 2 over 2. Okay? We have a negative root 2 over 2. Okay? If we went to a negative 5 pi over 4, that would be right here.
same thing.
You're going to get the same value. It's going to be a negative root 2 over 2. Okay? And that's what we're saying here. If I take the cosine of a positive 5 pi over 4, I'm going to get the same thing, a negative root 2 over 2, that I would if I took the cosine of a negative 5 pi over 4. Okay?
So, like, it says there that, like, the cosine of, like, negative u will equal cosine of u, which is, like, positive. So, like, do you change it to positive, like the answer to positive, or do you leave it as negative?
No. The angle is what's changing sign. The value of the trig function just is what it is. The angle is the only thing that's changing sign. So here's the thing. How this can be used is if you're asked to find, hey, what's the cosine of a negative 11 pi over 6, and you're thinking, whoa, that's on the circle, but I'm having trouble thinking that through, you could just say, oh, well, what's the cosine of a positive 11 pi over 6? Yeah, that's root 3 over 2. Basically, in the cosine and the secant, you could just ignore the negative inside, because it's not going to make a difference. Okay? Now, the reason for this, and this is where the name comes into play, is that cosine is what's known as an even function. All right? An even function.
Cosine?
Cosine is. All right?
The other two are odd.
I'm going to color code all this so you can follow it.
Isn't it the same thing with like other functions too, like parabolas and
There are y equals x squared is an even function.
absolute
Okay?
values and things,
The absolute value function is an even function. That's correct. Okay? Well,
right? So
what is an even function?
where it's symmetric on both sides, right?
On both sides of?
The y-axis.
Exactly.
Is it the y-axis or their axis of symmetry?
Well, to be even, it has to be the y-axis. So if you shift a parabola over,
Oh,
it's not even anymore.
Yeah.
Okay? This is symmetric. Where are you going? Okay? These are functions that have symmetry across the y-axis. And that's because the value of a function at x will equal the same thing as the value of that function at negative x. Okay, that's what we're doing here. We're taking the angle, making it negative. It's going to give us the same value for cosine or secant.
So odd function would be sine.
And tangent.
Sine and tangent are odd functions.
They do
Okay?
not have symmetry.
Now notice here, they have a different type of symmetry. Okay? Let's look at sine and tangent. Notice that when you make the angle negative in either sine or tangent, what does it do to your value of the trig function?
Makes it negative.
It makes it the opposite as well, okay? So let's look a little more closely at the graphs here, okay? Our sine curve, again, I'll do 2 full periods. Here's 1 period, here's 2 periods, okay? For our sine curve, if I did, say, the sine of pi over 6, what does that equal?
1/2. No, root 2.
Yeah, no, 1/2.
No, it's 1/2.
It is?
Yeah.
Yeah.
It's 1/2,
It's 1/2.
okay? So it's 1/2.
It was supposed to be yeah.
But let's take a look at negative pi over 6, which is the same as 11 pi over 6, right? But negative pi over 6,
Negative 1/2.
negative 1/2, okay? So you see here, there's a similarity, okay? But it's got the opposite value of sine, okay?
They're odd functions.
So these are odd functions, okay? An odd function is one where we call it symmetry, but it's actually like a double reflection, which, if you remember back in geometry, a double reflection actually gives you a rotation. If it's a double reflection across intersecting lines. So actually, it's a reflection across the y-axis and then the x-axis both. And we have what's called symmetry about the origin. Okay?
So if you shifted it, it wouldn't work anymore.
Yeah, if you shift it, it doesn't work anymore. But notice what happens here. If I take this sine curve, all right, and I take it and let me change the color on it so we can see it a little easier. Okay? If I take that sine curve, its symmetry about the origin means if we rotate this thing 180 degrees,
It's the same thing.
it's the same thing. Now, my drawing isn't perfect, but you can see there, we get the same thing when we rotate it around the origin. That's why we call this symmetry about the origin. And the key here is that f of negative x is going to equal the opposite of f of x. Okay? That's the definition of something that is an odd function. Okay? So, if you remember that and you picture your trig functions, it's easy to remember which ones you have to rotate for symmetry. Because like if you had tangent, remember tangent looks like this, I'd have to rotate that 180 degrees to get it to line up with itself. Okay? Tangent and sine are the odd functions, and those are the ones where a negative angle makes the value negative. Okay? Cosine has symmetry across the y-axis, so that's the one where making the angle negative has no impact on the value of the cosine. Okay? So, that all being said, I'm emphasizing this for two reasons. One, it's new and it's helpful to take some time with it, but what you're going to find real quickly is that we're going to use the reciprocal, quotient, and Pythagorean identities a ton. You aren't even going to have to really try to memorize those. We're going to use them so much, you're just naturally going to memorize them real quickly. The cofunction identities and the even and odd identities we will use, but it's not as much as the others, so you're going to need to take the time to actually try to memorize them, okay, so that when you need them, you remember that you have them, okay? So that's partly why I was taking a little more time here in class to go over that. Now, why are we learning these? There's 4 key applications that we're going to look at, or already have looked at. 1, you even had one of these on your test, so we'll do one more just to refresh our memories again. We can use it to evaluate trig functions, okay? We can also use it to simplify trig expressions, and basically we're going to spend the rest of today and a lot of next week just doing number 2 here, okay? Then we'll also look at developing additional trig identities and then solving trig equations. And really all 3 of these applications are going to tie in to this last one, okay? So we're able to solve any, no matter how sophisticated it is or whatever, we're going to be able to solve it, okay? Now, let's do one of these to kind of refresh our memories. This is what we're talking about, using identities to evaluate trig functions, okay? Now, we looked at how you could use identities or you could use triangles to do this, but I want to focus on doing this one here just with the identities, okay? So first thing here, we're told that the secant of u is a -3/2 and tangent is positive, okay? And we want to find the other 5 trig functions. So first things first, what quadrant are we in?
Third. First or the third? No, we have to be in the third because secant's negative.
It's gotta be the
Secant's negative, okay? So yeah, tangent's positive in the first and third,
Secant.
okay? But secant's the reciprocal of cosine, and cosine is negative in the second and third, so we've got to be in the third quadrant here, okay? We're in the third quadrant. Alright? So, that tells me that, hey, my cosine's going to be negative, sine's going to be negative, cosecant's going to be negative. I got all my negatives taken care of, so I don't need to worry about forgetting them anymore. Okay? Now we can focus on what the values of these things are. So what would be easiest to find next?
Cosine.
Cosine, it's a negative 2/3. What identity did you use?
The reciprocal identity.
Good, the reciprocal identity. The reciprocal identity. Okay? Where do we go from here, though?
Sine squared plus cosine squared equals 1.
Good. Sine squared plus cosine squared is 1. That's a what kind of identity?
Pythagorean.
Pythagorean. Good.
Pythagoras.
Okay? cosine is a negative 2/3, so cosine squared is 4/9. So that means sine squared equals 5/9. Good. And then you square root, and sine of u, good, square root of 5/3. Now, understand when you square root in an equation like this, it could be positive or negative. Plus or minus the square root, but
It's gotta be minus.
very good. We know it's got to be the minus one, okay? So it's a minus root 5/3. Yes?
Could you have used 1 minus cosine squared u equals sine squared?
Yeah.
That's what I don't.
What else can we find next? Okay, cosecant. That's going to be
3 root 5.
The 5 or 3.
3 root 5/5. Okay? It's 3 over root 5, and then you rationalize 3 root 5/5. Okay? So now we just have tangent, cotangent.
Tangent is square root of 5 over 2.
Very good. Sine over cosine. The thirds and the negatives are going to cancel out, so it's root 5/2. You used a quotient identity there.
So you could do 2 root 5/5.
And then great, we have a 2 root 5/5 for our cotangent. Okay? So you see how if we just know one of them and we know what quadrant we're in, we can get the other 5. Okay? In fact, the one I gave you on the test, I forgot to tell you a second piece of information. So you could have either had these negative or the tangents negative.
Okay.
There were 2 possibilities for that one. I realized
I
it
was so confused on that question.
afterwards, so.
Extra
Wait, say
point.
that again?
I didn't tell you the second piece on
Oh.
the test. So technically you could have had the negatives with your sine and cosecant or with your tangent and cotangent. As long as you didn't put negatives on everything, then
I was so
Okay.
confused
So.
on that. I was like,
It's
you can't do it because it could be in either of these
you
two
can't. You
quadrants.
said more than one possibility. So you guys got it fine,
Every
I'm sure.
answer
So
that exists.
all right. So now we're getting to number 2 here, and we're simplifying the trig expressions. Okay.
Oh, I like this.
These are fun. These are fun because everyone's like a little puzzle that you got to figure out. Okay. So the idea here is we can use some algebra and we can use our identities to write this in a much simpler form. Okay. So you guys thinking whether by identity or by algebra, what could we do to this thing?
You can't cancel out the sign x's.
We
No,
can't
it's a
cancel out the
fraction.
sine x's. Okay, yeah, we could do that.
What did she say?
Yeah.
Make that
say
cosine
equals-
squared into a 1 minus sine squared.
Oh, true.
Now, we chose to do this. We can't cancel out the signs, but we could have factored it out. We could have factored out a sine, and we would have had cosine squared minus 1 in the parentheses. But we're going this way, and that's fine.
Just we distribute them.
So good, yeah, we can distribute. So we have sine x times 1 minus sine x times the sine squared, so that's going to be a
Sine cubed.
sine cubed x, good, minus sine of x. So what does that equal?
Sine x.
Negative sine cubed x.
That's
Yeah.
0.
Um,
And there we have it.
question. Where you got negative sine cubed?
We distribute.
Oh, okay.
So yeah, we have negative sine cubed x. And here's the thing, if you had factored out the sine first and done some other stuff, you would have gotten the same place.
How would you factor out the sine?
You could have done sine x equals cosine squared x minus 1. And you'd have to be careful here because it's a 1 minus cosine squared equals sine squared. So since it's backwards, it's going to equal a negative sine squared x. And then that'll equal a negative sine cubed. Okay? So either way is totally fine. It's whatever you see. And that's why I like these a lot, because you'll get, 4 different people doing 4 totally different strategies, and they all work a lot of times. Okay? Now, a little snapshot of why this could be useful. You're going to see how this is useful in solving equations, but also if you're going on to IBSL, or you're going on to IBHL, or AP Calc, or Calc Honors, you're going to do derivatives. Okay? Now, I don't expect you to understand what's going on here, but it's going to be obvious which one is easier to work with. Okay? If I'm finding the derivative of this original form, I actually have to use something called the product rule and then something called the chain rule and do some other stuff.
Oh, that's a lot of stuff.
Okay?
That's a lot of stuff.
And
there's more stuff. Okay.
notice I do eventually use a Pythagorean identity in there as well.
Eventually.
But check it out. This whole thing goes down to a -3 sine squared x times cosine. Don't write this down.
Who's
Okay?
looking forward to calculus
All right.
next year?
But since you guys know how to simplify this down to negative sine cubed of x, I can use something just called the chain rule and write down the answer without even having to do all of that. Okay?
Yeah, that looks
And I know you guys don't know calculus yet, but you can count. And 1 step is less than 5 steps. Okay? So it's helpful, alright? It's going to be really helpful. And when you get to integrals, it's even more helpful, because integrals are more of a challenge. Okay? So,
Wait, so how we get from there?
don't worry about it right now. You'll learn in calculus if you take calculus. Alright? So,
next year.
one other example here I want to work our way through here. And this is, you're asked to verify the identity. And I want to give you a rule here. Okay? Oh, I forgot a rule back here. It's not really a rule, it's more, I'm going to give you kind of some key things to remember. When you see a trig function squared, you may want to write these down like all in one list as we come across them. When you see a trig function squared, think Pythagorean identities. Okay? Think Pythagorean. Whether you see a sine squared, a cosecant squared, a cotangent squared, you're not necessarily always going to use a Pythagorean identity, but when you see a squared trig function, think Pythagorean. Okay? So, now, here's the rule when you're told to verify an identity. Okay? You're told to verify an identity. You cannot assume it's equal. Okay? You're being told to prove this equals this. So, since you're not allowed to prove it's equal, or you're not allowed to assume it's equal, do not use algebra. Okay? In other words, you may say, hey, cosecant's 1 over sine, so I'm going to multiply both sides of the equation by sine. You can't do that. Alright? You can't do that because we don't know if these are equal yet. We don't know if this even is an equation. Alright? So, we just have to work with the sides individually. You're allowed to do stuff to both sides. You could write this as 1 over sine if you want. Okay? But you cannot take something from one side to the other. Okay? Now, I'm going to leave that there. What do you propose we do with this left side?
Feature the second part of the conversion.
We could. We
Does
could.
that help?
That's where the trial and error aspect of this all comes in. Okay? It in fact won't in this case, but that's not a bad thing to try.
Turn 1 plus cosine theta to negative sine and then put that as -1.
We can't, you're trying to use the Pythagorean identity, right? But that only works if you've got squared.
You can
Can't
separate it.
Can't you square
separate it. Separate the fraction.
Okay?
Sine over 1 plus sine over cosine.
You can't do that when it's in the denominator. You could do it if it was 1 plus cosine over the sine, you could split it, not when the addition's in the denominator.
Question, so not use algebra, but we can use all identities and.
Oh, yeah.
Could you like make it like change denominator to numerator?
Yeah, make the denominator
Yes.
the same.
Negative.
Yeah, get a common denominator, alright? So here, we're going to multiply this fraction by sine over sine. We're going to multiply it by sine over sine. So we have sine squared over sine times 1 plus cosine. You say, well, why didn't you distribute? Unless you see a specific reason why it would be helpful, don't distribute. Okay?
Factor out later.
Yeah, because chances are you'll end up factoring it out later. This one, we're going to multiply by 1 plus cosine over 1 plus cosine. Okay? So that's going to give us a cosine plus a cosine squared. And it's over sine times 1 plus cosine as well. So I'm going to put this all in the same fraction now. Because I have a common denominator. Yes?
I just found an easier way.
What?
Like you change the numerator to denominator, the first one, make it negative 1 plus cosine over sine.
Just flip this?
Yeah, make it negative.
You can't. You can't just take a reciprocal.
You can make it like negative 1 plus cosine over sine.
No, you can't.
That'd be awesome.
You can't just.
Because the result is right. So you try it.
Well, just because you end up in the right spot doesn't mean you necessarily got there in the legal way.
But
I mean, there may be a way. You can't just do that. There may be a way where if you do some other stuff, it may end up that way, okay? But you can't just, oh, I'm just going to flip this and make the 1 negative. Okay? But listen, hey, how do we finish this? Take a look. Sine squared plus cosine squared is 1. So this is a 1.
1 plus.
I have 1 plus cosine theta over sine theta times 1 plus cosine theta.
1 over sine.
And check this out. If I look at this as 1 times 1 plus cosine, that and that equal 1, and I'm here. Okay? So.
So would it just be cosine?
Have a nice day.
Yeah.